Hello, this is our science teacher Tim Martin, and in this astronomy video we want to talk about novas and supernova. Also, we can talk about this as the death of stars, because sometimes stars do interesting things when they die. Before we get into the death of stars, it may be good to review and recap how a basic star evolves. So it starts out as a nebula, a large cloud of mostly hydrogen gas. Gravity is at work and pulls that nebula together into a protostar. As the pressure and temperature increase, the protostar may be rotating. Once the temperature reaches 10 million Kelvin, nuclear fusion begins and we have a main sequence star. It's important to remember that there's an equilibrium at this point between the nuclear explosions trying to blow up the star and gravity trying to crush it. These nuclear reactions for a typical Sun-like star may last approximately 10 billion years, as the star fuses hydrogen into helium. As the hydrogen fuel runs low, pressure will increase in the core of the star. This causes the temperature to rise. As temperatures near 100 million Kelvin, helium fusion may begin in the core, with hydrogen fusion happening outside of the core. As the star swells and surface cools, it becomes a red giant star. After the star exhausts its fuel supply, it will shed its outer atmosphere in a planetary nebula. As the atmosphere expands away, the white dwarf is the glowing core that remains. This no longer has nuclear fusion going on, and it may glow until it cools off in something like 20 billion years. That's for a typical Sun-like star. But like I said, sometimes stars do interesting things when they die, so let's examine that. What if we have two stars side by side? Well, chances of two stars being exactly on the same life cycle is a little rare. One star may actually become a red giant before the other, but then they both may become red giants. Well, if one became a red giant first, it likely will go into planetary nebula and white dwarf phase before the other, and this is where it can get interesting. Because the neighboring star can shed some of its solar wind or some of its atmosphere onto the neighboring white dwarf. Keep in mind that neighboring white dwarf is still extremely hot, temperatures in the 100 million range. So if a significant quantity of hydrogen piles up on the white dwarf neighbor, it may restart fusion, and that will give us a nova. So, what is a nova? And a few important facts of novas. They only occur in binary systems. This is not something that we will risk with our star because we are a single star. One star will go on and become a white dwarf, and the companion red giant will dump material off onto its neighboring star. When sufficient hydrogen builds up, it may restart nuclear fusion, but this time, rather than having the nuclear fusion in the core, it's happening right on the surface of the small white dwarf. When this happens, the star may flare 1,000 times brighter for several days, and then it will calm down and continue its normal existence. This process can repeat many times as long as the situation exists where the red giant is neighboring a white dwarf in close proximity. But sometimes stars do even more interesting things when they die. Let's start out with a large nebula, and gravity will work on it to become a large protostar. The large protostar may become a blue giant. The blue giant may become a red supergiant, and the red supergiant could end its life violently in a supernova explosion. So, let's explore the supernova explosion. Once again, we start with a nebula. That leads to a protostar. That can lead to a blue giant star, which will lead to a red supergiant star. And all of this is fairly similar to what goes on in a normal main sequence star. The supernova is quite different, so let's explore this last stage of the evolution of supermassive stars. So with these large giant stars, we have a blue star as opposed to a yellow or red star. But similar to a normal star, nuclear fusion is happening in the core. Hydrogen is fusing to helium, helium is fusing to carbon. Really, the only difference is it's happening much more rapidly. Keep in mind, all of these nuclear reactions are exothermic. That means they're giving off significant amounts of energy. And again, this is requiring temperatures up to around 100 million Kelvin. Unlike a normal main sequence star that may last for 10 billion years, a supergiant star may live its entire existence in a few 100,000 or maybe a million years. At the point of helium to carbon fusion, the star will expand. Now, when I say expand, I really mean the star will expand. Here's a red supergiant. The relatively close star Betelgeuse in the constellation Orion is 430 light-years away. We can see it easily in this image taken in my backyard. With the powerful telescopes at the European Southern Observatory, we've actually been able to measure the size of Betelgeuse. It's truly massive. When we say supergiant, it's incredibly large. Here you can see the innermost circle is the orbit of Mercury, followed by the orbit of Venus, Earth, and Mars. Even the planet Jupiter's orbit would be within Betelgeuse. In fact, Betelgeuse's size almost extends to the orbit of Saturn, nearly 2 billion kilometers across. So, with these supermassive stars, down in the core, gravity and pressure is increasing significantly. And when I say rises, I'm talking now about 600 million Kelvin up to nearly 3 billion Kelvin. Fusion will continue. We'll see a layer where there's helium fusing to carbon, another layer where carbon fuses to oxygen, another layer where oxygen may fuse to neon, and neon fuse to magnesium. Magnesium can fuse to silicon and sulfur. Eventually, the silicon may fuse to iron. It's similar to an onion-like structure, as there are different layers of fusion happening throughout the core of this star. Keep in mind, all along, this star is in equilibrium. Gravity is working to try and crush the star, the nuclear explosions are forcing outwards, and the star is in balance. But at the point of iron fusion is endothermic rather than exothermic. Rather than giving off energy, it takes in energy. So instead of having the forces in balance, now they're both directed inward, and the star will undergo something extremely dramatic. It's at this point that the iron core will collapse. When it collapses, all the layers sitting on top of it also collapse, and it explodes in a violent supernova. The atmosphere is blown away as it falls and then bounces off of the core. Many heavy elements throughout the periodic table are fused in this shockwave as it rips out through the layers of the star. For several weeks, the star may be as bright as an entire galaxy or a billion stars. There was a well-known supernova explosion that happened back in 1987. It was only visible from the southern hemisphere, so I never got the chance to observe it. Do you notice the star in this field? Well, neither do I, until that day in February when it blew itself apart and we could see this star outshining all the others. As we look around the sky, there are leftover remnants of many supernovas. The Cassiopeia A supernova likely occurred in 1680. These are its leftover remnants. Supernova 1604, often referred to as Kepler's supernova, has been studied across the spectrum from X-ray to optical to infrared light in this composite image. Supernova 1999 was an interesting one in the Black Eye galaxy. There it is, outshining the billions of stars in the core of the galaxy. There was a supernova that happened in the spiral galaxy M74. I had a chance to observe this one back in 2002. Actually, it didn't occur in 2002. It occurred 35 million years earlier. Only the light from this exploding star reached Earth in 2002. One of the most famous supernovae is the one that occurred in the year 1054. This is now known as the Crab Nebula. Ancient Chinese astronomers recorded that a guest star appeared. It was so bright it could be seen in the daytime for 3 weeks. This is a well-studied object. This high-resolution black and white image was taken at the Palomar Observatories in 1950. In this 2005 image from the Hubble telescope, we can see that the gas cloud has expanded. Let's take a look at that again, because we can still see the expanding gases even though the explosion was first documented on Earth over 1,000 years ago. We've studied the Crab Nebula across the spectrum, in radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, and even in gamma rays. By studying it in these various portions of the spectrum, we've learned a lot about what's going on inside and what the leftovers are after these violent supernova explosions. Speaking of leftovers, it depends on the size of the original star. We may be left with this bizarre object called a pulsar, or possibly even a black hole. Thanks for watching, and I hope you join me again as we explore more about the evolution of stars.